Hello, I'm Roman, and welcome back to another video in the series Let's Learn Neural Networks from Scratch in Go. And this is the series of the videos where we dive into the bare bones of neural networks using this fantastic book that is called Neural Networks from Scratch, but in Python. But we will use the Golang here. So let me show you this book. Where is it? It's called Neural Networks from Scratch in Python. But again, we'll use the Golang just to make things harder for us, well, for myself. And in the last video, we finished this Introducing the Neural Networks book or chapter. And basically, we took a look at what the neural network is and how it's similar to brains neural networks. This one will start from chapter 2. I'm not sure if I will be able to finish the whole chapter today, but I will start. This one is named Coding Our First Neurons, and hopefully this is what we're going to do. And to begin, we will be using, well, at least in the book, they will be using the Python 3.7, although any version of the Python Plus or Python 3 Plus will likely work. We'll also be using NumPy after showing the pure Python method and the matplotlib for some visualizations. And if replacing the Python is not a big deal, well, it's not a big deal, but replacing the NumPy will be a little bit challenging. But I mean, this is the goal of this course, well, of these videos. Since this is the Neural Networks from Scratch in Python, book will demonstrate how to do things without NumPy as well, but NumPy is a Python's all things numbers package, and I would say that the NumPy is probably top one package that is used for anything related to numbers calculations and like working with the vectors, matrices, and doing lots of that stuff. In between videos, I found an alternative for some stuff for the Go. So once we will finish with this pure implementation, I will switch to the Go num, I think the package it's called, but we'll see. So let's go. A single neuron. Let's say we have a single neuron and there are 3 inputs to this neuron. As in most cases, when you initialize the parameters in the neural network, our network will have weights initialized randomly and biases set to 0 to start. And as we saw in the previous chapter, the weights and the biases are the trainable parameters. So this is what is actually changing during the model training. Why do we do this will become apparent later on. We're just going to make up values to start with a single input for now. So, okay, let's just replicate it as it is. So we have inputs, which is plot, okay, 64, 1, 2, 3, and okay. So we have our inputs. Each input also needs a weight associated with it. Inputs are the data that will pass into the model to get the desired output, while the weights are the parameters that we will tune later on to get these results. Weights are one of the types of value that change inside the model during the training phase, along with the biases that also change during the training. The values for weights and biases are what get trained. We'll start by making up weights for now. Let's say the first input at index 0, which is 1, has a weight of 0.2. The second input has a weight of 0.8, and the third one is negative. So, okay, let's duplicate. Let's replicate it. Minus. Can I do this? Oh yeah, nice. Next we need the bias. At the moment we're modeling a single neuron with 3 inputs. Okay, so we're modeling the neuron network with a single neuron. And we also need a bias. So bias to... Okay, so this is what will represent our... do we have this? Okay, so let's assume this is this neuron. So we have the well, I think we have this with 3. No? Let me check. Okay, well, this is the 4, but so we represented the neuron, this one. So we have the input value. So this is the first one, this is the second one, and imagine that we have the third one. We have each connection has its weight, and plus the hidden layer will have a bias. And then this one. This neuron sums each input multiplied by that input's weight, then adds the bias. All the neuron does is take the fraction of inputs, where these fractions, weights, are adjustable parameters, and it's another adjustable parameter, the bias, then output the results. Our output will be calculated up to this point like this. Okay, so basically we need to go through all of the inputs. We need to take a value, multiply it by the weight, sum it, and output. Okay, bias. I mean, I don't want to write this with like this. Okay, let's... We'll assume that the inputs and weights had the same lengths. Can I do the plus equal here? Let's try. Multiply it. So we have the result 2.3, and we had the same. And the output should be here 2.3. We will use these arrows to denote output in this book. Okay, so this is what we have. Well, this is the weight somewhere. This is the input value. Here it's a sum operation, and it adds the bias, and it outputs the results. Yeah, let's take a look. But I think we already know how it works. But I actually like watching these animations. They are really good. I mean, they're good in terms that they visually explain pretty much good. Okay. Yes, and this is how we end up with 2.3. Okay. What might we need to change if we have 4 inputs rather than 3 we have just shown? Next to the additional input, we need to add an associated weight, because like with the new input, it means that we will have another connection from another input, or maybe from another neuron to this one. Next to the additional input, we need to add associated weight, which this new input will be multiplied with. So, okay, 2.5. Oh yeah. Hello, Go. And bias 2.0. So yeah, they again using the indexes, but we are a little bit better. So the result is the same. Cool. Okay. So this is our neuron, right? Okay. Neural networks typically have layers that consist of more than one neuron. Layers are nothing more than the group of the neurons. Each neuron in a layer takes exactly the same input. The inputs given to the layer, but contains its own set of the weights and its own bias, producing its own unique output. The layer's output is the set of each of these outputs, one per neuron. Let's say we have a scenario with 3 neurons in a layer and 4 inputs. Okay, so we're doing outputs for the layer of the neurons is actually an array of results for each neuron, right? Okay. We'll keep the initial 4 inputs and set of the weights for the first neuron the same as we've been using so far. Okay. We have the same inputs. Then we have weights, 3 weights and 3 sets of the. Okay, let's how it's type neuron. We have weights. Justin, can I do a dynamic array? Bias expected type. Oh. Okay. So Then we need 3 neuron. Let's call it neuron 1. And bias 2. Missing type in composite link. Okay. Can I do this? Okay. Okay. Oh no. So this is the first neuron. This is the second, right? And 3. Then the output should be yeah. So we have our inputs, we have 3 neurons, and we have the outputs. And the output should be an array of 3, right? And actually we can do neurons and 1 and 2. Can I do this? Expected appearance neuron. Okay, so we have our neurons. Okay, and the next thing we need to calculate the outputs. So what we're going to do. First, we need to go through all the neurons. Right. Outputs. Then again, we're doing the same for k less than inputs. And oh, come on. Can I assert? Ooh, really? Is that? What's equal to use a package assert not in selector. Okay, make the same. Declare but not use. Okay, we need to sum up the inputs k divided by weights. No, not in one. Neuron weights. Okay, then equals new. Okay, let's remove it for now. We'll just assume that it's the same. And once we have it, we should outputs. So, okay, we declared 3 neurons. We went through all of the neurons. We calculated the value for a specific neuron. Inputs weights, okay. Added the bias, and let's check 4.8, 1.21, 2.385. That's cool. That works. That worked the same. The only difference that it's a little bit nicer than this one with all of the indexes and the specific variables. We can declare as much as neurons as we want. Neurons. Okay, let's take a look at the math. It said that it's not storing this setting for the embedded videos. 3. Yeah, but I checked it before, right? Okay. Code, math, and visual behind. Yeah. In this code, we have 3 sets of the weights and 3 biases, which define 3 neurons. Each neuron is connected to the same input. The difference is in the separate weights and bias that each neuron applies to the input. Yeah. This is called a fully connected neural network. Every neuron in the current layer has a connection to every neuron from the previous layer. This is the very common type of the neural network, but it should be noted that there is no requirement to fully connect everything like this. Actually, I thought that in every neural network, everything is connected with everything, like all of the neurons from... Interesting. Okay. Even that, I thought that if the neural network is kind of stretched horizontally with lots of the layers and very small amount of the nodes, it's still connected with everything. Okay. Imagine at this point we have only shown code for a single layer with very few neurons. Imagine coding many more layers and more neurons. This would get very challenging to code using our current methods. Instead, we should use a loop to scale and handle dynamically sized inputs and layers. We have turned the separate weights variables into a list of the weights. Okay. Yeah, so basically, well, they listen into the list of the array, well, list of the lists, or array of arrays, or two-dimensional array, vector for the biases, and again for the... and yeah, they use, like in the Python there is a cool function, and in other languages I'm not sure if Go has something like this. I think no, at least in the default library. So here's the deal with the zip. It takes two sequences and it returns the tuple that you can extract, and you will take, for example, the first element from this array and corresponding first element from the second array. If they have different lengths, then it will use the shortest length. So this is very convenient for us. I mean, for the goal, or at least for this one, I have to check manually because, for example, if, for example, for some reasons the inputs will be more than the weights, then I can have the index out of the range issue. Okay. Yeah, this is basically what I wrote. This does the same thing as before, just in more dynamic and scalable way. If you find yourself confused at one of the steps, print, it's not the zip, we're not interested. That's it. How do we know we have 3 neurons? Why do we have 3? We can tell we have 3 neurons because there are 3 sets of the weights and 3 biases. When you make a neural network of your own, you also get to decide how many neurons you want for each of the layer. You can combine however many inputs you are given with however many neurons that you desire. As you progress through this book, you will gain some intuition of how many neurons to try using. We'll start by using trivial numbers of the neurons to aid in understanding how neural network works in their core. Yeah, and for example, if we'll need something more complex, I mean, the bigger neural networks, it will be very hard to declare it with the code. So maybe we'll come up with some sort of a text file where I will be able to define just weights. Well, where I will be able to define just the parameters, and then we can load it and use it. Okay. With our above code that uses loops, we can modify our number of inputs or neurons in our layer to be whatever we wanted, and our loop will handle it. As we said earlier, it will be a disservice not to show NumPy here, since Python alone doesn't do matrix, tensor, array math very efficiently. But first, the reason the most popular deep learning library in the Python is called TensorFlow is that it's all about doing operations on tensors. Okay. Tensors, arrays, and vectors. What are tensors? Tensors are closely related to arrays. If you interchange tensor-array metrics when it comes to machine learning, people probably won't give you too hard of the time. But there are subtle differences, as they are primary either the context or attributes. What? There are subtle differences, and they are primary either the context or attributes of the tensors. Okay, to understand the tensor, let's compare and describe some of the other data containers in the Python things called it. Well, let's start with the list. Okay, list of the list. Okay, everything so far also be an array. Everything is shown so far could also be an array of array representation of a tensor. The list is just a list, and it can do pretty much whatever it wants, including... Okay. The above list of lists cannot be an array because it's not homologous. A list of lists is homologous if each list along a dimension is identically long. This must be true for each dimension. So basically, for the tensor, I think we assume that every inner array had the same length. So for example, there should be 3 elements, not 2. Okay, matrix is pretty simple. It's a rectangular array. it has columns and rows, it's two-dimensional, so a matrix can be an array. Can all arrays be matrices? No. An array can be far more than just columns and rows, as it could have 4-dimension, 20-dimension, and so on. Yeah, that's true. So we call a matrix only a two-dimensional array. And I guess homologous two-dimensional array. The above list could also be a valid matrix because of its column and rows, which automatically means it could also be an array. The shape of this array would be 3 by 2, or more formally described as the shape of 3, 2. Okay. To denote a shape, for example, these neurons, if we will represent it as a tensor, it will have the 3 by 4. Interesting how it will handle. Well, okay, we're ignoring the biases. To denote a shape, we need to check every dimension. As we already learned, a matrix is a two-dimensional array. The first dimension is what's inside the most outer brackets, and if we look, we can see 3 lists here. Okay, yes, that's the second one. This is the third one. The size in this dimension is 3. Each of those lists has to be the same shape to form an array, and matrix is in this case. The dimension size is the number of the elements inside this more inner pack of the brackets, and we see that it's okay. Okay, so this is basically an explanation that if we take a look at the first array, consuming that every element is something, so we'll have 3 elements, which will give us 3. Then we take a look inside and we see there are 2 elements, and it gives us 2. If somewhere we will have, for example, here we will have 3 elements, then it wouldn't be a tensor, and it wouldn't be a matrix. 3-dimensional arrays, like in LOL, below, will have a third level of brackets. Yes. Okay, and well, how many? Got the first one because yeah, it's really hard to parse. So I guess we have 3, 2, and 4. Oh, okay. 3 to 4 dimension. Finally, what is a tensor? When it comes to the discussion of tensors versus array in the context of the computer science, pages and pages of debates. Okay. This intense debate appears to be caused by the fact that people are arguing from entirely different places. There is no question that a tensor is not just an array, but the real question is, what is a tensor to a computer science in the context of the deep learning? We believe that we can solve the debate in one line. A tensor object is an object that can be represented as an array. A tensor object is an object that can be represented as an array. I mean, why wouldn't call it just an array? Oh, okay. I guess I'm not sure if I would agree. I mean, even from what I read, there is a certain expectation for this array. So for example, the second dimension should have the same shape for all of the items. Another way, it will be just an array of randomly sized arrays. So for me, the main thing about the tensors, it's just all of this. What this means, as a programmer, we can and will treat tensors as arrays in the context of deep learning. And that's really all the thoughts we have to put into. Are all the tensors just arrays? No, but they are represented as arrays in our code. So to tell us they are only arrays, and this is why there is so much argument in the but okay. Okay, for me, it's just tensors are just a way to name. I mean, this is just a special terminology for the deep learners, because I think from the computer science perspective, they definitely different in terms of the math and the science behind the machine learning. But from the software engineering perspective, it's just an array. I mean, with a couple of conditions, but it's still an array. In this book, we define an array as an ordered, homologous container for numbers. By ordered, and mostly use this term when working with a NumPy package, since that's what the main data structure is called within. Linear array, also called a one-dimensional array, is the simplest example of an array, and in plain Python, this would be a list. Okay, linear array, one-dimensional array for the Python, or for the NumPy. The list arrays also consist of multidimensional data, and one of the best known example is what we call a matrix in mathematics, which we will represent as two-dimensional array. Each element of the array can be accessed using a tuple of indexes as a key, which means that we can retrieve any array element. Okay. We need to learn one more notion, a vector. Simply a vector in math is what we call a list in a Python, or one-dimensional array in NumPy. Of course, the lists and NumPy arrays do not have the same properties as a vector. Just as we can write matrix as a list of lists in Python, we can also write a vector as a list or an array. This is in contrast to physics perspective, where the vector's representation is usually seen as an error characterized by the magnitude and the direction. I mean, but it still will be a one-dimensional array, right? I think that's the main difference is how you treat the data and how you work with this. Oh, dot product and vector addition. Okay, here we go with the math a little bit. Probably the main difference why they talking about that there is a vector, because again, as I told, it's how you treat the data. Because array, I would assume vector multiplication and array multiplication will be different things in terms of the algorithm. And that's one of the most important operations we'll perform on the vectors. We can achieve the same result as in our pure Python implementation of the multiplying each element in our inputs and weights vector element-wise by using a dot product, which we'll explain shortly. Traditionally, we use dot product for vectors, yet another name for a container. And we can certainly refer to what we're doing here as working with vectors, just we call them tensors. Okay, so not one size. How it's called? The one lens shape is a vector. Nevertheless, this seems to add the mysticism of the neural networks, like there are these objects out in a complex multidimensional vector space that we'll never understand. Keep thinking of vector as arrays. A one-dimensional array is just a vector. Because of the sheer number of variables and interconnections made, we can model very complex and non-linear relationship with non-linear activation functions. And truly feel like wizard, but this might do more harm than good. Yes, we will be using the dot product, but we're doing this because it results in a clean way to perform the necessary calculation. It's nothing more in depth than that. As you've already seen, we can do this math with a far more rudimentary sounding words. When multiplying vectors, you either perform a dot product or a cross product. A cross product results in a vector, while a cross product results in a vector, while a dot product results in a scalar. First, let's explain what a dot product of two vectors is. Mathematically, mathematicians would say, okay, dot product between two vectors. So we have, okay, I guess what we actually did here was the dot product. Yeah. Yes. We have a sum of multiplications between corresponding elements. For example, a1b1, a1b1 plus a2b2. So this is what we actually did. We can call it dot product between two vectors. A dot product of two vectors is the sum of products of consecutive vector elements. Both vectors must be the same size, have an equal number of elements. Yes. Let's write out how a dot product is calculated in Python. For it, you have two vectors, which can represent the list, blah, blah, blah. Okay, dot product is... Okay, so... I mean, just to make it so we can do this, we can call it dot product, right? And we'll have vector 1 as float as an array, vector 2 floats 4, and it returns a scalar, right? Missing return. So we're taking this, right? So we're defining the why. Okay, maybe like this. Output 0. Return outputs and can't use output variable of type, but so we can do output is like dot product between inputs, neuron weights, plus bias. Neuron, right? And use input. Can I do this? And so this should give me the same result. Correct. Now, what if we called, A inputs and B weights? Suddenly, this is the product. This dot product looks like, I have no idea how to pronounce this. Way to perform this operation we need and have already performed in plain Python. We need to multiply our weights and inputs of the same index and add the result values together. Okay. We'll also need to perform a vector addition operation in the not too distant future. Vector addition. Okay. Fortunately, NumPy lets us perform this in a natural way using a plus sign with variables containing a vector of the data. This addition of the two vectors is an operation performed element-wise, which means that both vectors have to be the same size, blah, blah, blah. Okay. The result is a vector calculated as a sum of the consecutive vector elements. Okay. This is the vector addition operation, and there is a cross product. Okay. Single neuron. Let's code the solution for a single neuron to start using the dot product and the addition of the vectors. Okay, np dots. So it's a dot product. We have it implemented in our own way. Yes, so plus bias, plus bias. Okay. So what is the next? I will quickly check. Oh, and this is actually the power of the Python and the NumPy. The weights here is the array of the arrays, but still you can use dot product and you can pass weights and inputs and plus biases. And because they, this is actually, so np dots will return array like this of the outputs, and then it will add the biases afterwards. Okay. A batch of data. To train neural networks tend to receive data in batches. So far, the example input data have been only one sample or observation of various features called a feature set. Okay, bunch, okay, matrix. Okay, so what we've done today, we checked. I will leave this batch of data matrix product transposition layers of neurons and batch of the data with NumPy. What else? I'm just checking how long it until chapter 3. Okay, so I will continue with the rest of the second chapter tomorrow. So I will start from a batch of the data. We'll see how it will work without NumPy, because NumPy provides you some flexibility which we would not have. But we'll see. Maybe we'll start using, I found this GoNum, and this is, GoNum is a set of the packages designed to make writing numerical and scientific algorithms productive, roman and scalable. contains libraries for matrices and linear algebra, statistics, probability, sampling, and so on. So probably we'll start from replacing the weights and the inputs with stuff from the GoNum. Or maybe we'll do it once we go through this second chapter, but we'll do it tomorrow. But for now, thank you for watching, and I see you tomorrow.